Okay, it's 3 p.m. Thanks to everyone for attending this seminar and taking the time. We'll kick off this year's series of Wolfram Technology seminars with a talk on the newly released version of Mathematica, which is version 13. This version was released in December, just the same as version 12 was released in December of 2020. So we will, each new year now starts with a new version of Mathematica. Before we talk about Mathematica 13, let's just introduce ourselves. The company I work for is called Unisoft Plus. We are a small technical company based in Austria in a very small town called Perg. The company has grown to 30 employees now, most of which are theoretical physicists, mathematicians, and software engineers. What is our relationship to Wolfram? The company has been reselling Wolfram technology for more than 20 years now. We are serving the German-speaking parts of Europe, like, for example, Austria, Germany, and Switzerland. And our largest customers are the Austrian universities, the Fraunhofer Gesellschaft in Germany, and we also have site licenses with some commercial companies. The services we provide is license and installation support for Mathematica and all the other Wolfram technologies. That means we support the customer from the point of ordering Mathematica until it is successfully installed on the machine. And once you have a running version on your machine, we provide technical support. But here, since Mathematica has grown into such a complex technical tool which covers so many fields, we are only as good as we can, and for many fields we have to rely on the Wolfram company in the US and in the UK for supporting our customers. The other areas that we serve is we are doing data science. Here we are heavily invested in, for example, the Hortonworks Hadoop-based technology stack, which is based around Java. But we also use Python, and of course we also use Wolfram in doing data science. Another field is industrial mathematics, where we do projects where we do classical simulation and modeling. And in financial mathematics, we have our own product, which is called Unrisk. This is a product for doing risk management with Mathematica. Now let's move on to Mathematica 13. Mathematica 13 has been released in December 2021. And a good start is always to look at the number of built-in functions in this version. And you see here with version 13, around 500 functions have been added to the system, and 500 functions have been updated. And if you look at this graph, you see that there's a really nice linear growth in the number of in the available functionality in the Wolfram system, starting from version 1, which was released in 1988. And you also see that, for example, this newest released version adds as many functions as were initially available in the first version of Mathematica in 1988. The agenda for this talk is, before I talk about the agenda, I want to point you to a very good seminar series, which is part of Wolfram U. This seminar series consists of 5 different seminars which cover topics such as video computation, machine learning, calculus and algebra functionality, geometric computation, cryptography, visualization, and geovisualizations. And these are all topics which will not be discussed in this talk. I'm trying to focus this talk on new features in Mathematica 13, which are usable for any kind of Mathematica user, and which are also I'm personally interested in. The first one is we'll talk about Mathematica installation, which has changed in version 13. Then we will look at what's new in the notebook interface. We'll then look at a feature which is now complete in version 13, which is called Wolfram Packlet authoring. We'll look at what's new in the core language, in the core Wolfram language. Then we'll look at how to use trees in version 13, which have been added as first-class objects now. And finally, we will wrap up this seminar with a Q&A session at the end. What are the supported Mathematica platforms? As you probably all know, we have Mathematica supports Windows, Linux, Mac OS X, and also the Raspberry Pi. On the Windows side of things, Windows 11 is now officially supported as an operating system. Windows version 13 has dropped support for Windows Server 2016. So if you want to use Mathematica 13 on Windows Server, you have to upgrade your Windows Server to 2019. And a very important feature in the front end for the Windows version is that the font rendering under Windows now uses a new API, which is called Direct Write. And this allows for much better rendering of fonts, meaning better subpixel rendering and better anti-aliasing. So the quality of the rendered text is now much better in this new version. On the Linux platform, there you find the regular updates for the major distributions like Ubuntu 21, Red Hat 8, CentOS 8, the latest versions of OpenSUSE and Fedora. Version 13 has dropped support for Ubuntu 16, which is still in use. So if you are using Ubuntu 16, you have to at least upgrade to Ubuntu 18 now. On the Mac, Apple this version now, version 13, adds official support for version macOS 12, which is called Monterey. It's also the version of OS 10 that I run on the machine I'm giving the presentation on now. And one very important feature for Apple macOS is that version 13 now supports Apple Silicon natively as a universal binary. If you have used version 12.3 before, you probably know that there were two different versions, one for the Intel and one for the Apple Silicon, and this caused a lot of confusions upon installation. So now Wolfram has rolled these two versions into a single universal binary, which runs on both architectures on the Mac. Finally, on the Raspberry Pi is not released. Version of Mathematica is not released in lockstep with the other versions. So the Raspberry Pi version is still at 12, and we can expect version 13 later this year. Mathematica 13 is one of the new versions which brings a different installation process. Wolfram has now separated the installation into an installation of the program and an installation of the documentation. If you go to your user portal and go to the download section there, you will actually find now 3 different installers. One is called Mathematica and Documentation. This is the regular, this is called the bundle installer, and this is the regular installer which installs both the Mathematica and the documentation. Then you have Mathematica Web Documentation Only installer, which only installs the program but not the documentation. And you have 2 separate documentation installers, one for English and one for Japanese. And one important pitfall that you should be aware of is if you download the bundle installer and then run the normal setup to install the Mathematica, there is now an additional installer which installs the documentation. That means when you're done with the regular installation of the program, you have to manually launch the documentation installer in order to get the documentation installed on your machine. If you prefer not to install the documentation, you profit from a nice reduction of the needed disk space. For example, on my machine, the Mathematica 12 took around 12 gigabytes of memory, and this has now been reduced to 6 gigabytes in version 13. So if you have a notebook with an SSD where memory is very precious, you may consider not installing the Mathematica documentation. And if you do that, Mathematica will actually use the web documentation, and any kind of documentation lookup that you do will then go to the web version. That means you have to be online in order to use the documentation. What's new in the notebook interface? One nice feature is that Mathematica 13 now automatically enters paired delimiters. The front end automatically matches delimited that open and close expressions, like, for example, brackets, braces, parentheses, association delimiters, comment delimiters, and string delimiters. For example, if I type here a square root, and immediately when I then type the opening bracket, the front end will immediately automatically insert a closing bracket. And if I start a list, it will immediately add a closing list delimiter. And I can, for example, then, the same is true, for example, if I start a comment here, it will automatically add the needed comment delimiters. This is a very nice feature which you probably know from other editors, and it's now available in the Mathematica frontend. If you do not like this feature, you can go to the preferences and disable it in the, there's a new setting called automatically insert matching delimiters while typing. And this controls the behavior of the front end. Another nice feature is that the front end now supports code ligatures. What is a ligature? A ligature is a term from typography, and a ligature occurs when where two or more letters are joined to form a single symbol. For example, if you have this sequence of characters here, then you can transform it into a ligature, which is actually then an arrow. Or, for example, the greater equal sign can be replaced by a single symbol, which we all know from math, which uses this combined notation here. And the Mathematica 13 frontend preserves exactly what you type, but only changes the appearance, and it uses ligatures to change the appearance. Like, for example, in December, I'm starting typing A, then I start with an arrow. Then Mathematica immediately replaces this with an arrow ligature. I can then, for example, also start doing a path lookup, like so from a vector, and I start to use the bracket notation. And immediately, if I then enter the second bracket, the front end replaces this by using this special bracket notation, which is used for vectors. And if I go, if I use the cursor keys on the keyboard to go back into my expression, you see that the front end automatically expands the created ligatures, so that I can really easily make changes without having to resort on entering special characters on my keyboard. And this special option is controlled by a cell notebook option, which is available in the option inspector. If you want to change this behavior, go to the format menu, open the option inspector, and there you can then find the auto operator renderings settings. And you see here, this is the option that actually controls which kind of sequence of characters are replaced by ligatures. Like, for example, here, this is the function ligature. This is the arrow is used for rules, and so on. There's also in version 13, there's also a more user-friendly interactive iconizations. That means if I use, for example, iconize on a range, there is now a small plus sign next to the iconization, and this iconization then gives me some important information about this iconized expression, like what is the head of the expression, what is the expected, what is the length of the list, and what is the actual byte count in the expression which is stored in the notebook. Another feature is that parallel computing now progress monitoring is now much nicer. Longer computations display information about the progress and estimated time of completion. Let's just look at an example. Here I'm starting a parallel table, and you see that when the parallel table runs, I have a nice progress dialog where I can see exactly what is going on, which evaluations are running on the kernels, how much time has elapsed, and when the computation is expected to be finished. And this is all always updated in time. This feature is supported for all kinds of parallel computations, like, for example, parallel map, parallel scan, and all the other parallel commands from the parallel computing toolkit. A major new feature in version 13 is that creating Packlets with version is now possible. What are Wolfram Packlets? Wolfram Packlets are self-contained units of Wolfram functionality that can be integrated seamlessly into the Wolfram environment. Packlets have been added to the Wolfram system almost 10 years ago, I think, with version 9 or version 8 even. And they were only recently partially documented in version 12. And now with version 13, their integration is what I would call them feature complete. These Packlets can be discovered, installed, and updated automatically by the Wolfram system. What is a Packlet? Physically, a Packlet consists of a directory tree that contains Wolfram language code, documentation, library link libraries, JLink libraries, Java libraries, or executables, which form a self-contained part of Wolfram software, which then runs in the context of the Wolfram system. This directory can be compressed into a single file with the extension .packlet, which is then a convenient form for distributing and installing. For example, Mathematica itself is distributed as a combination of many Packlets. The Mathematica 13 Lite includes over 270 Packlets. I can, for example, find all the Packlets installed on the system using this Packlet find function. And this will actually tell me that there are 273 Packlets installed on my system here. But Packlets may also be stored outside the Wolfram Mathematica installation directory. There are two special directories, the $base packlet directory and the $use packlet directory, which are located on some folders on the system. And it's not uncommon to have multiple different versions of the same packlet installed on your system. For example, if I look at the neural networks packlet, here I have many different versions installed on my system. And if we look at the location of these Packlets, you see that the most recent version is actually shipped with Mathematica 13 here. And these other Packlets here are Packlets which have been auto-updated by the Wolfram system from the Wolfram servers. And Mathematica automatically chooses the right version, which is the one with the highest version number. Many of these Mathematica Packlets have a feature flag which is called auto update. That means anytime you run a function from these Packlets, Mathematica will actually check back with the Wolfram server if a new version of that Packlet is available. And if this is the case, the new version will be downloaded to the system. This is also a way the way that Wolfram uses to ship, for example, important bug fixes in Packlets that ship with standard Mathematica installations. And now with version 13, for the first time, you have all the tools available to create Packlets in Mathematica. There are two things that have been added to the system. The first is a package called Packlet Tools, which we can load here now. And there's this Packlet Tools package contains a function to create the Packlet. And this Packlet I'm going to create this Packlet in my Wolfram Documents directory. I'm going to open this. This creates a Packlet layout in the directory. And if I open the Finder now, we can then inspect this created Packlet. You see that it created a few files and folders. Let's just look at the Packlet info.wl file here by opening it in the front end. And here you see, let me just blow this up a little bit. Here you see, for example, this is a special file which contains meta information about the Packlet. Here you specify the name of the Packlet, the version of the Packlet. You specify the Wolfram versions, that means the Mathematica versions that this Packlet is compatible with. And then an important part is the extension sections, which specifies in which way this Packlet actually extends the Wolfram system. Here we have, for example, an extension of the kernel. That means that this Mathematica code is marked as with the expansion kernel. That means here we say that here we describe that the Packlet creates a context containing my Packlet, and the root of this Packlet is the kernel directory. It also adds documentation to the Wolfram system. For example, if we had installed library link libraries or other things, we would also have just let me mute this. If we had added Wolfram libraries, we would have a declaration of Wolfram of them here. Let's look at the other file in the Finder. This is simply a Mathematica Packlet that has been created by the system. Packlet. Let's also blow this up here. And here you see this is simply a Mathematica package file, which simply declares a function. The function is called say home, and this package infrastructure is actually functionality that modifies the naming and symbol lookup in Mathematica. And this makes up a package. And we can now, we have now created an initial packlet. And if we do a Packlet find here, you see that it doesn't find the Packlet. That means during development, the Packlet is not located in the regular Packlet lookup directories. That means we have to add our Wolfram Documents directory, our development directory to the actual session. We do this with this Packlet directory load command. And if we now do a Packlet find here, you see that it actually finds our package, and this is exactly the package which is located here. You can load it with needs and run the say hello function, which is part of the myPacklet package. And the great thing about version 13 is now that Mathematica 13 allows for the generation of Packlet documentation without having to use the Wolfram Workbench. The Wolfram Workbench is a rather old tool which was released 15 years ago, and it was based on the is still based on the Eclipse development environment, which was a very popular development environment at that time, but now has somewhat fallen out of fashion and is not no more used widely. And the problem always was that the Wolfram Workbench for Wolfram Mathematica users always was a quite alien environment to do development. And now with version 13, the documentation generation has been completely revamped and can be done completely now from within the front end. In the front end, a new documentation tools palette was added. This documentation tools palette existed before, but it has now completely been revamped in this release. And here you see here I have the Add Packlet button, where I can simply add my existing Packlet, which has just been created to the Packlet, to the palette. You have to confirm this Packlet addition and then I can, what this does immediately is, if we go to the Finder, it immediately has created a documentation directory with the needed skeleton for reference pages, guides, symbols, and tutorials. And I can now use, for example, the new function page to create the documentation for a symbol, which, for example, the say hello function, and say OK. This creates a template for this say hello function, where you then can add basic documentation, like this function says hello. And I can add more documentation in here. I can add references to other documentations here in the tech notes. Actually, there are three kinds of documentations. There are function or symbol pages. There are guide pages which contain references to other pages, and there are tutorials or tech note pages which contain give a tutorial or a basic explanation about technical things of your package. And all these can now be done from the documentation tool palette you have in this documentation tool palette. You also have, for example, different commands for doing formatting. You have commands for adding links to other pages which are part of your documentation, for adding links to URLs which are available, for resources which are available on the web. And you have, of course, you can do formatting, like code making transformations to the different texts. This is all was available before and has been revised in this edition. And once I'm done with my documentation, I can now use a new function called Packlet documentation build, which then builds this documentation and transforms it into a form which is suitable for distribution. This starts a process which creates a compiled documentation. And here, as a result, you see exactly what has been done, which files have been processed. And you also see, if we go back to the Finder here, you see that in the build directory, a new build directory has been added, which now contains the build documentation, which is now in a special format, which is needed so that Mathematica can, so that this Mathematica documentation can be integrated into the Wolfram system. And the final Packlet, which is this .packlets file, can then be built with using the Packlet build command. This Packlet build command looks at all the files and then creates the Packlet archive in the build directory. This is this file here, which has now been created by the build process. And this is the final package which is suitable for distribution. And how can this file now be distributed? If you have access to this file via file system, you can simply deploy this packet by using the Packlet install command and given a path to the build file. I can do this here now. This actually installs the Packlet on my system. if I do a find Packlet now, then you see actually that then multiple Packlets are listed on my system now, because of course I have the one which is stored in the development location, and I have the one which is installed in the library folder of my machine. And if I can, of course, I can use the Packlet here. I can use the say hello function, and I can do a Packlet uninstall, which removes the Packlet from the library folder here. But I can also deploy this Packlet automatically to the Wolfram cloud. I'm simply connecting to the cloud, and here I'm using the copy file command to copy this file to a cloud object which is created on the cloud. Let me do this now. This actually uploads the file to the cloud and gives me then a cloud object, which is a handle to this Packlet in the cloud. I can use the set permissions now to make this thing public. And if I can then, for example, very easily use the Packlet install and this will actually then download the Packlet from the cloud and install it on the system. Actually, it doesn't work now because I have already installed the local version of this Packlet on my machine. But I'm pasting this command here to the chat, so that if any one of you runs a Mathematica session, you can now simply run this command and you will have this Packlet automatically installed on your machine from my Wolfram Cloud account. There's a very nice talk about Packlet development available on YouTube. This talk is from the Wolfram Technology Conference from last year, and here you learn about much more all the details of Packlet development, much more than what I could tell you now in this small overview. For any kind of mathematical developers, this opens a completely new way of distributing Mathematica functionality, because up to now most of the functionality was distributed as Mathematica notebooks. Now you can really wrap up your existing developments in Mathematica packages and then create Mathematica Packlets from these directories, these directories, and really distribute them easily from your cloud accounts. Let's now move on what's new in the core language. Mathematica has, from version 1, supported something called contexts. And in the new version, a new feature has been added, which is called context aliases. When you use Mathematica, you actually work with different symbols, and Mathematica uses a concept called the context path to look up the definitions of these symbols. And if you, for example, load a package using the needs command, what is actually happening, that this new context, like for example your computer arithmetic, is added to your context path, and then all these names which are exported from the computer arithmetic package are then usable without qualification from your session. For example, I can use the arithmetic function, which simply returns some information about the computer arithmetic on my machine, and this symbol is found by querying the context path and using the first package where this symbol is exported. The problem with this approach is that this is a form of using global names, and if you do development in other languages, you probably know that using global names is a bad habit, and this may make your programs fail in the future, because what may happen, arithmetic is another generic name, and it may be that Wolfram adds this arithmetic name as a system function, and then what you actually get is a shadowing conflict, which may break your program in the future. And what could you do? What you always could do to avoid these problems is use the full form or the full name of this function. Like for example, you can computer arithmetic and use the tick notation here to address the arithmetic function. The problem is that this is way too verbose. And with Mathematica 13, there's now a new way to work around this problem by using a feature called context aliases. For example, when I'm using the general utilities packages here, I can establish a context alias which is to be used for names from this package. This general utis will then be, let's have a look at the context path. You see that using this context alias notation results in a context path that has not been changed. That means the general utilities package has not been added to the context path, but it has been added to a new global path, which is called the context aliases path. And I can now address these functions by using the aliases. All context handling functions have been updated to support context alias. That means, for example, if I want to look up the names which are contained in this general utis package, I can use now the context alias, and it will automatically be replaced by the actual context name, which is general utilities. And I can also in the Mathematica notebooks, I can then use this short context alias, which may often consist of 2 or 3 characters to actually run the function. And once I'm done with using the function, using this general utilities package, I can simply unset the context aliases for this context alias, and then the computed this function here from the general utilities package will no longer be replaced, will no longer be available on the system. So really, this is a major step towards making your programs future-proof. And this is also something that is common in other programming languages, where you can use short context shorter names to replace longer names. Another hole that has been fixed in the core language is that the extract function now supports generalized position specifications. Mathematica has always supported a part function which used this shorthand notation here to extract a part from an expression, like for example the second element from the list here. And these part specifications could be generalized to, for example, I could use the symbol all to extract all the parts of the expression, or for example, I could use a span expression to extract, for example, every second element from this list. And the extract function exists since Mathematica 3.0, and the extract function is different in the form. Part is a very immediate structural operation, and extract is a more traditional functional form. In this form of only supported regular indexes here, like for example 2, and now in version 13, you can also use symbolic expressions like all and span. You can also extract multiple parts in one go, like for example, if I pass here a list of span expressions, I can extract multiple parts in one go, and this gives me ACE and BDF, for example. And another feature is that I can also apply a function to the extracted parts immediately. For example, here a total expression here applied to the extracted parts. And this lets me write very high-level code, which only makes one trip to the kernel, but does very many things in one round trip to the kernel. And unlike part, one advantage of the extract function is also that it supports the operator form. That means I can form these nice functional pipelines here using the postfix notation, where I can, for example, here then extract the functions and run the square root functions on the result. And if I used the part expression here, I would have to resort to using a lambda function, which is not as elegant as the extract form which we saw here above. Another feature which I've personally waited for a long time is the support of importing ISO timestamps with embedded time zones. If you any kind of sane software now creates date and timestamps in the form of we choose this ISO 8601 form, which consists of the date in this form separated by and the time separated by a T character, and it may have an optional time system character at the end. For example, the character C denotes the Greenwich Mean Time, and if I can, the from date string function now is capable of interpreting these time zones. And if I'm having an explicit time zone here added to my timestamp using the plus function, using the plus +02, this is also supported now. And the resulting data object expression uses the local time zone on my machine by default. And if I want to use a different time zone, like for example, I always want to my data objects to use the GMT, then I simply can pass a time zone option, which then affects the output time zone of the date here. Here the time zone is now GMT. And of course, the reverse conversion is also doable using the date string function and using the ISO date time format, and the separator C lets me produce an ISO 8601 compliant timestamp. And I can also create a time string with an embedded explicit time zone using this date string format here. And for versions before 13, one could use an external Wolfram repository function, which is just embedded here into this notebook as a reference. But it's now really a nice feature that this is finally supported in Mathematica 13. Times have received another new feature. The new Mathematica 13 adds support for different time systems or standards. What is a time system or standard? This is actually a physical is a standard that indicates the physical process that determines how the measurement of time advances, and it is based, for example, on atomic oscillations, on the rotations of the Earth, or some astronomical phenomenon. If you do a research on Wikipedia, this is actually really a science of its own. And if you from programming, you probably know that date and time handling, what seems very easy on first sight, is actually extremely complicated when you go to the nasty details. There are two very famous blog posts available on the web, which I've referenced here, which is falsehood programmers believe about time. For example, one of these falsehoods is that, for example, a day has 24 hours, or that a minute has 60 seconds. These are all false assumptions. And there are even more. There's even a blog post which follows this up with more falsehoods. And now with Mathematica 13, you can really use more exact time system than the default, which is called standard civil time in Mathematica. If you use the automatic time system, the date object has now received a new option called time system, which is now set to automatic, for example, by default. And this just gives us the regular standard civilized time. But this time system is not capable of, for example, of representing leap seconds. In the years, for example, in the year 2016, this was not only a leap year; it was also a year where leap seconds were added to the final day. That means actually we had on the final day of the year, the last minute had 61 seconds in the minute. And with using this time system UTC, I can now accurately, as you see by the notation here, I can now accurately represent this kind of time information in the Wolfram system and do computations on it. For example, if I convert this back to the standard civil time, which is not capable of representing leap seconds, it will simply drop this 1 leap second from the timestamp, and we have now a representation which is not as accurate, but probably accurate enough for most applications. There are even more. One of these supported time systems, for example, is the International Atomic Time, which is measured by using data from about 400 atomic clocks around the world. And this International Atomic Time is currently 77 leap seconds ahead of the GMT time. For example, this date here is actually we would have to add additional leap seconds to have a really accurate date. And these time systems are now supported in Mathematica 13 and allow for much more precise date and time computation than what was possible before. Another one of the, in my view, best new features of Mathematica 13 is now that trees are supported as first-class object. What are trees? Trees are fundamental data structures in computing to represent nested structures. We all encounter these nested structures in everyday work, like, for example, you have a corporate hierarchy structure where you have a board at the top. Below there are executive officers. Below you have vice presidents. Vice presidents then have managers, and managers have employees. We all know files and directories are hierarchically organized. We have volumes. These volumes have directories. These directories can have other directories, and these directories can also contain files. And also the syntax trees in languages like XML and JSON are actually tree structures. Even a Wolfram language expression, of course, is a tree, is structured as a tree. Many file formats are tree-based, like, for example, Word documents, PDF documents, HTML5 files. And also in many computations, the actual states in the computation form a tree. Like, for example, in a game, in a chess program, for example, the actual each move creates actually a game tree where each move is related to another game position in the tree as a parent. And also you have, for example, decision trees in machine learning. Also, for example, in compression, you may have Huffman trees. So this is a very basic and uniform data structure which is now available in Mathematica. Before version 13, Mathematica has had somewhat limited support for trees. For example, you had the tree form where you could, for example, present a tree form of a Wolfram expression. And we also had support for graphs, which graphs, as you probably know, graphs, a tree is a special form of an undirected graph in which any two vertices are connected by exactly one path. That means if you have a graph, for example, here with a cycle, then you probably know that this graph is not a tree. And we also had the tree graph function, which let us determine if this graph is a tree. We could also create graphs which are strict trees, and then the tree graph function would tell us that this is actually a tree. But now with version 13, Mathematica has added new functions to the systems, and these functions let us construct and represent trees. It lets us do recursive traversals of these trees. It lets us perform computation of these trees. And of course, you have all these high-level functional programming constructs available that you know and love in Mathematica programming. What is the canonical representation of a tree? You use the symbol tree as the head, and then you have two elements here. The first one is the data in the root or in the node of the tree, and then you have a list of children. For example, a very simple tree with two leaves is presented here. And here you see that the default standard form for a tree is really a graphical representation of this tree. And the tree has simply a root node and two children. You can construct, of course, multi-level trees by nesting tree expressions. Here, for example, you create a tree with 5 nodes. And this is a tree which has here one root X, and it has as children another tree, which is this tree here, and a regular child, which is shown here. And the node data in a tree is optional. That means we can also have a tree which only consists of a list of children. And this means we can, for example, construct trees which only hold the data in the leaves of the tree. The inner nodes of the tree are empty. On the other end, we can also represent a leaf with no child. That means we construct a tree and set the list of trees to none, a list of children to none, and this gives us a degenerate single node tree. Of course, you can also use different tree layouts using the tree layout option here. A simple selection of these tree layouts is top, right, bottom, and left, which results in the following rendering of the tree. There are even more available, but you can look this up in the documentation. The most important function for the construction of trees is the function nest tree, which gives the tree obtained by applying a function to the data in the leaves of a tree and then extending the tree. Let's just look at an example. Here I have the nest tree function. This nest tree function here must return a list, which is the list of children, and it is applied to this root node here, and it goes. We do the nesting for 2 levels. If I run this function, you see that here actually, since this function only creates a list with 1 element, it creates a degenerate tree, which is just a single linked list. If I add, for example, here an F2 function, and then do the expansion again, you see that then it really creates a tree where we have two children. The first one is created by running the f function, and the second one is created by running the f2 function, and this is then applied recursively to the other levels. We can simply increase the number of levels here by increasing the number here and get a more greater, a deeper tree here. For example, one possible application is the Wolfram language system supports something called the Wolfram knowledge repository, where we can, for example, look up information about the world, and one of these information is information about persons. Like, for example, we can look up information about the Queen Elizabeth II of England, and this lets us, for example, look up her children by using the children property. And the Wolfram knowledge base tells us that she has 4 children: Prince Charles, Prince Anne, Prince Andrew, and Prince Edward. And for example, using this entity framework, we can now create a children function. This children function will, given an entity here, look up the children of this person and then filter all the persons which are entities themselves. And we can then, for example, apply this function to Prince Charles and see that his 2 children are Prince William and Prince Harry. And using the nest tree function now, we can simply apply the children function to the queen and do this up to her grandchildren, and we get sorry, this is okay. This didn't work. Okay. Sorry, this was. Let me just quit the kernel here. And do this again. Look up the queen. Okay, define the children function and then apply it, and then apply it to the queen. And here we see we get a nice tree where we see her descendants, like, for example, her children and her grandchildren. In the real world scenarios, we will encounter 2 file formats which are tree based. The first one is XML. XML can be, let's just look at an example here. For example, here I have an XML document which contains a database of the most expensive paintings here. And if I do an import of this XML, I actually get a symbolic XML representation. And this symbolic XML representation contains a lot of syntactical sugar, which is completely irrelevant for the types of computations that I mostly do. And I can now, by using the tree feature, I can now clean up this symbolic XML by simply defining an XML data function, which extracts the data for the nodes, and an XML children function, which extracts the data for the children from the XML element tags which are contained here. And then I'm using the nest tree function again, and I'm using the XML data function to extract the data for the nodes, and the XML children function to extract the data for the children. And here I've also set the tree layout to a special layout called balloon embedding, which produces which actually moves the node of the root of the tree to the middle of the graphics, and then you have the immediate children at the periphery of this image. Here, for example, we see that one of the most expensive paintings is from Jackson Pollock. And another one is, for example, from Gustav Klimt. And this, of course, the other important data format that you will encounter is JSON. Here we can do the same. Here we have an example JSON document which describes some form of smart contract. And if you do an import of this JSON data into Mathematica, you get something which is called a JSON rule list. And again, we can simply set up functions like JSON data and JSON children, which extract the required data from this rule list here. And if we do then a nest tree using the JSON children function and the JSON data function, and do this to infinity, we get the smart contract represented as a nice tree here. So this is really and the great thing about this tree feature is that it frees you from having to use with these specialized tree implicit tree structures that you encounter in real world. You can now really use an explicit tree and run all these tree functions that we are going to see on the next slide. There are also other construction of tree function, like for example, k-array tree creates a tree where each node has at most a specified number of children. For example, here we create a tree with 32 nodes where each node has 4 children. We can create also a random tree with a certain number of nodes, like for example here. We can also, a very useful function is if we have a nested rule set, which often encounter in Mathematica, we can use the rules tree function to create the rules tree from this list of rules. And of course, the inverted function is also available, which is called tree rules, which returns us the original representation as a list of rules. And of course, we can also use the expression tree function to produce an expression tree representation of a Wolfram function. This can be seen as a more modern version of the existing tree form function, which existed for a long time. Once we've done representing with importing a tree, we want to run computation on a tree, and the most important function which has been added here is called the tree map function. Tree map applies a function to the node of a data of a tree. If we have the tree here, for example, with this node section here, then when I run the tree map function here on the tree, you see simply, of course, that it does what you expect. It runs the function on each node of the tree. And we can, for example, do this on our queen example. Here we have the queen descendants again. And let's just say we want to actually replace this with the tree which contains the age of each of these persons. We define an age function which runs on the entity or person. We compute the date difference and use the Wolfram knowledge repository to retrieve the birth date of the person and compute the date difference to today in years. Then we can compute, for example, the age of the queen. And we can then, for example, map the tree age function to all the queen descendants and get a nice representation of this of the years. Of course, in the function, if you can, the data contained in the nodes of a tree can be an arbitrary mathematical expression. For example, I could, for example, here preserve the original information and then simply run the age function on the node, and then get a nice rule in the nodes which contains both the person and the name and the age as a rule list. So with the use of tree map function, you can compute augmented trees. That means when you have imported your data into your system, you can augment these tree nodes with data computed from the nodes of these trees. When it comes to trees, there is always the question: what is the actual computational traversal order that we use? We could, going back to the tree here, we could start here computation on the root node, but we could also start computations on the leaf node and then move up. We could, for example, do the computations in the childs in the left to right or a right to left fashion. Mathematica lets us do all these things by passing options to the tree map function. For example, given this tree here, I'm now using the echo function, which simply returns the original argument to the function and then returns the argument unmodified. And here I'm seeing how tree map actually the default traversal order that tree map uses. That means it actually does a depth first order with children visited before the parents. That means here, for example, if a tree map function has started with this node here, then moved to this child, then moved up to this tree, this node, then to this node here, and then finally to the root. This is the default traversal order, which is post order in a left to right fashion. But of course, Mathematica allows me to use any order of traversal. That means I can also use a pre-ordered traversal version in a right to left fashion. Here I'm starting with the root node and move down the tree to the children of this node. And another useful recipe for this is you can use the reap and sow function to actually get the nodes in a list. That means I simply run the sow function here and then here I reap what has been sown, and then this collects the sown data in a list. And so you can easily then, for example, transform the traverse tree into a list. Let's just now look at a real-world example. For example, let's just say we want to compute the succession to the British throne. If you look this up on Wikipedia, you will find that this is actually a very the succession to the British throne is determined by a different set of rules which consider descent, sex, legitimacy, and religion. For simplicity, we just look at descent now, and we already have our children function from before. The problem with this function that it returns the children in an arbitrary order. And you probably know that when it comes to royals, the firstborn child is usually the heir to the throne. That means we have to support these children by age, and we can do this simply by defining a children by age function. We use our existing children function and then simply use the reverse by sort by, which then use our existing age function to compute the age of the person. And if we apply this children by age function now to a person, we see now we have, for example, Prince William's children are then computed, ordered by their age, where the older child is returned first. And now we can create a tree where all descendants of the queen are ordered by age. And if we want to now compute a succession to the British throne, we can do so by doing a simple pre-ordered traversal of the descent tree. And this is done here by using the pre-order in a left to right fashion. And this gives us the succession to the British throne, starting with Queen Elizabeth. The next will be Prince Charles, then Prince William, Prince George of Cambridge, and so on. So if everything goes as planned, the queen will be followed by 3 kings. And you see here that the great thing about trees is that now we can really, instead of doing an implicit computation of these things, we can use the appropriate computation that Mathematica provides in a similar fashion. Where for example, we could do computations on graphs or on matrices. This is not doable for trees, and this is a great addition to the language. Just for completeness sake, I have also presented here a few other functions. There are functions for querying tree properties like tree data, tree children, and so on. There are modifying operations on trees like tree insert, tree delete, tree replace, and so on. These work in a similar fashion to the regular functions you know from the Wolfram language, like insert, delete, replace, and so on. The same is true for the pattern-matching functions like tree cases, tree position, tree count. And there are also tree conversion functions, some of which we have seen, like, for example, tree expressions and tree rules. This completes my presentation of Mathematica 13. And again, I want to have collected some important references on the new version. For example, here the summary of the new function, which is available on the reference documentation here. If you, it contains a detailed overview of all the functions which have been added or modified in this version. There is also the Stephen Wolfram's introductory blog post, which contains a good overview. There is Stephen Wolfram's Mathematica presentation, which is available on YouTube, which is rather long. And I personally can recommend John McClune's Mathematica presentation, which is 90 minutes long and really covers all the newly added features in a very nice way. This completes my talk, and I want to thank you for your attention. And if there are any questions, please ask them now.